Welcome back. Last time we started talking about feedback linearization. And remember we said when we looked at robust control, we played with systems of this form. And we said at the time, what was special about these systems is that the state, x, was composed of one scalar variable, small x, and then its derivatives up to order n minus 1. And we said that if this was the case, there's a u here, if this was the case, then if you assumed that f and b were exactly known, then you could do something quasi-trivial, which would be to call this entire right-hand side, to call it v, right? Then you would have the equation x to the n equal v. You would design a controller any way you know, for instance, just linear control, for instance. And since you know f and b exactly, once you have your control law v, you can compute uniquely a control law u that gives you the same v. Okay. So we said if the dynamics was exactly known, that's what you could do. And by the way, this is the analogy, indirect analogy to pole placement, right, in linear control, right, where you basically take a dynamics and you replace it by something else, okay, using feedback, okay. In the case of linear control, the dynamics is itself linear, and you do pole placement by changing the coefficients of the characteristic equation. Incidentally, so we also said that, of course, the reason we did robust control was that you didn't know f and b exactly, okay? And if you think of it, in the linear case, if you mess up a little on the parameters, it means you're going to move the closed loop poles a little away from where you wanted them to be. If you mess up a lot, you may move the closed loop poles in the right half plane. Okay, so that's where you have a robustness question in the linear case. In the nonlinear case, even more complicated things can happen, okay, which is why we said, we have to consider directly this question of robustness and address it as such. Also, a remark on this, which will be useful later on, okay. Suppose that somehow you get a controller that does exactly the job, okay? So you have a desired trajectory xd of t. You start at x equal xd, and you want to follow this desired trajectory, okay? And for some reason, somebody gave you a top-notch algorithm that does exactly the job, okay? Follows x equal xd exactly, okay? So can somebody tell me what the resulting control signal, the one that the actuator would see, u of t, which itself is a function of the state and so on, but the actuator sees a signal, right? What would this u of t be, right? So I'm saying the control does a top job, okay? Whether or not you know f and b, it follows the desired trajectory exactly, starting on the desired trajectory. What would u of t be? Well, it would be the unique solution of what? Of xd to the n is equal to f of xd, the vector t, plus b of xd of t times u, right? Right, which gives you, of course, xd minus f divided by b, right? Okay. So in other words, if you have a system in this form, there's a unique control signal that does exactly the best job, right? And it could be computed this way. Now, why don't we do it this way? Well, precisely because f and b are not known exactly, and you want feedback, and you want all these good things. Okay? So when, for instance, when we consider robust control at the limit, something like pure sliding control, right, and we say it gives you an exact trajectory tracking, it means that through this process of switching and perhaps approximating and so on, right, we're getting very close to this unique solution. But in the presence of uncertainty, possibly large on f and b. All right? But it's something important to remember in a sense, because the fact that the perfect solution is unique, okay, then you have to come up with it somehow through an algorithm, right? But the perfect solution is unique. Which incidentally says, if you have things like actuator bounds or things like that, that perfect solution should verify them as well. Okay, so we said when we consider the system in this form, what was special about them was the state, which in turn, we could see that, by just a change of variables, a change of what we mean by a control input, the designer input, we could make it look very simple. Now, we said the whole topic of feedback transformation or feedback linearization is about just how general is this form. Okay, if you don't start with this form, if you don't start with something like f equal ma, can you transform the system in this form? Okay, and that was this whole topic of feedback linearization. And we said, just by hand, just by playing with simple examples, we said that there are 2 points of views. Okay, one is we take our system and we try to find a state transformation so that in the transform state, it just looks like something like this, right? The state is x dot x to the n minus 1, the transform state. And the last equation is x to the n equal v. Okay, so we can do it. So we saw on a simple two-dimensional example, we did this by hand, okay? And we found a way to do it. Or we didn't convert to x to the n equal v, we convert to a second order linear time invariant system, which of course then can be converted in something like this. And we said, well, since what we really care about having a state in this form, there's another point of view, which is, as I said, as in the Google I feel lucky point of view, which says, let's start with the signal x of t we care about, and let's differentiate it. And at some point, we'll find a control input. Okay? And you can show more precisely if it needs exactly n differentiation to find a control input, then essentially you're done, because precisely you'll have transformed the system in this form. On the very simple assumptions, it cannot take more than n. Okay, so you'll find it at n, right? But if you find it before n differentiations, it means that basically you could do this, but then you'll have some leftover dynamics, right? Because basically you'll stop at the 14th differentiation in the 20th order system. You'll do everything based on your 14th order system, and you'll have a 4th order thing floating around, okay, which will be subjected to the same input, and therefore you still have to worry about it. Okay, you still have to make sure it doesn't blow up and things like that. It doesn't have to tend to 0. It doesn't have to do precise things, but at least it shouldn't blow up. Okay, it should remain. Okay. Now, to try and understand a little more what was happening, and also because this whole line of research which says consider exact dynamics, how can we transform them into something like this? Okay. We said this whole line of research is about extending linear ideas. Okay. We said, well, let's see what this looks like on linear systems. Okay. So on linear systems, we picked 2 quasi-trivial second-order systems. Okay. One was x dot 1 is equal to x2 plus u, and x dot 2 equal u, and the other one was x dot 1 is equal to x2 plus u, and x dot 2 equal minus u. Okay, so this was system 1, this was system 2. And we said, suppose we care about controlling x1, then we will only, based on this idea of differentiating until we find the input, well, here we have it, right? So if we care only about controlling x1, we could design a controller based on only the first equation. And because the first equation is the same in these two systems, if we design a controller based on only the first equation, it will be the same controller. Okay. However, this control input also applies to the second equation. So we have to see what's left, basically what happens to this leftover term. Okay? And we saw in this very simple case that this worked. And this didn't work. Okay? In other words, x2 was unstable. Okay? So, and then we said, if we just happen to look at the transfer function, x1 over u, we'll see that this transfer function is minimum phase, in this case where it works, and in non-minimum phase, in this case where it doesn't work. Okay, so in other words, if we happen to compute the transfer function, here you'll have one right half plane zero. Well, you'll have only left half plane zeros, and here you'll have one right half plane zero. So we said, well, could this be a general result? Okay, that this kind of very simplistic point of view of I take the input, I differentiate until I get the control, I design based on this, and I forget about the rest of the system. Could this actually work in the case of minimum phase systems? Okay? And intuitively, right, the difference between minimum phase and non-minimum phase systems, right, is that minimum phase system says that the inverse system is stable, right? It has no, the zeros are left half plane, so the inverse system is stable. So it means if x1 behaves, then u behaves. Okay. While here, the non-minimum phase, the inverse system is unstable because you have a right half plane 0. And therefore, even if x1 behave, in general, u doesn't. Okay, so that was the intuition. So what we're going to do now is show this result much more generally for linear systems, okay, and then see what can we do to extend it to for nonlinear systems. Okay. So that's the story. Any questions so far? All right. So we're still in the introductory section of this chapter, right? Then later on, we're going to state formal results without proving them, just stating them and see what they mean, right? And these results will require, tools in differential geometry. And to really understand these results, you would have to first kind of take a course, or at least a few lectures on differential geometry, which we won't do. Okay? But we're still in the introduction, just trying to understand the basic ideas. Okay? And so we are at we're still at section 613. So, consider a linear system given by some transfer function, z over u, scalar, okay, scalar input, scalar output. So this linear system could be, coming from something like a state space representation. Or equivalently, without allowing for any pole zero cancellation, a transfer function representation, b0 plus b1s plus bmsm over some general, so let's call them a0, I guess. Yeah, a0 plus a1s plus ansn. Okay. Or maybe just to simplify, plus an minus 1 Sn minus 1 plus just Sn. Okay? We'll absorb any coefficient of Sn in the numerator. So this is, you just have a transfer function, you know, poles and zeros. So numerator polynomial or denominator polynomial times u. Okay. So we have n poles, of course. And of course, n is the dimension of the state, okay? And we have m zeros. And n minus m is what's called the relative degree of the transfer function, or the relative order of the system. It's the difference between the number of poles and the number of zeros. Okay? So, we can, based on this transfer function, we can put this system in companion form, in controllability canonical form. Okay. The idea, or one way of doing it, is to rewrite this numerator as one block, and then the denominator as another block. Times u. Okay. And so how does the system look in companion form? Well, we have the usual, it's going to be a state. Okay. And the A matrix is going to be simply 0, 1, 0, 0, 0, 1, defining, you know, the companion form, the controllability canonical form. And of course, sorry, and it keeps going. And so on. Okay, so we end up with a matrix, an identity matrix of order n minus 1. And then the last line corresponds simply to the coefficients of the characteristic polynomial, so minus a0 minus a1 minus an minus 1. And here we put, okay, minus an minus, sorry, minus an minus 1. Okay. So we have dots everywhere, right? So we have the identity matrix. At the bottom, we have just the coefficients of the characteristic polynomial times x plus all zeros and just 1 times u. Okay? So that would be the way to put this transfer function in companion form. Okay? So we would get a column of zeros except for the last one, the identity matrix of order n minus 1, the bottom line just with the coefficients of the denominator of the transfer function, times x plus a B matrix, which is all zeros, and then 1 for the last one. Now, this is not enough for this system, because we still have this term, right? So we add a y equals cx kind of thing, right? And this z, therefore, is going to be equal to b0, b1, b m minus 1, 0, 0. Sorry, bm, sorry, times 0, 0. Right? So we have this transfer function here. We started putting this in a state space form, okay, where the first n minus 1 equation are just saying that the state is x, x dot, and so on, right? The last equation is the characteristic equation. But now, of course, we have to take this times that, and taking this times that means that we multiply with this, okay? Times x, of course. Everybody understands this, right? This is b0 times x1 plus b1 times x2, which is the same thing as x dot, plus b2 times x3, which is the same thing as x double dot, and so on. Okay, so we get this. Everybody understands this? Okay. So this is, if you want, the state space representation of this transfer function. Okay. And where we have put these zeros here, again using the fact that the state is just x, x dot, and so on. All right. So here we are. We started from this transfer function. We have a state space representation. Now the question, what we're going to do is we're going to say, okay, so z is the output of interest. Let's differentiate it until u shows up. Okay? So let's take this z here and differentiate it until u shows up. So what can we say about z dot? So we differentiate it once. Okay? So remember, z is b0x plus b small x plus b1 small x dot plus bm x to the m, right? So u is nowhere in there. Okay, so we need to differentiate to find u. Okay, so is that clear, right? This is just b0 x1 plus b1 x2 and so on, plus and so on, plus bm x m plus 1, right? Which is the same thing as b0 x1 plus and so on, plus bm x1 to the m. Okay? So what's z dot? So z is b0 x1 plus b1 x2 and so on, right? So z dot is b0 x1 dot plus b1 x2 dot and so on. So how can we write this? Yeah, we just shift. It's exactly like a shift register, right? So we have b0 x1 dot. So b0 comes here because x1 dot is equal to x2, right? Plus b1 x2 dot, but x2 dot is equal to x3, so b1, and so on, okay? And we end up with a bm and one less 0. Right? So it's exactly like a shift register, right? Because this is the derivative of this, and this is the derivative of that, and so on, right? When you differentiate once, you just shift. Okay? So originally, how many zeros, as in the number zeros, did we have here? N minus m plus 1, right? Because you have b0 to bm, right? So originally we had n minus m plus 1 zeros, okay? So if I keep differentiating, when I differentiate up to order n minus m plus 1, so n minus m minus 1, what do I get? So each time I differentiate, I push the shift register, right? I've differentiate n minus m plus 1 times, okay? N minus m minus 1. Where is the shift register? Where is this block of b's? It's all the way there, right? Because that was exactly how many slots I had. So you have bm here, and bm minus 1, and so on, all the way to b0. And then you have zeros. Okay? Each time I differentiate, I shift one notch, okay? So I differentiate n minus m plus 1 times. I've shifted all the way to the end. And there's always an x, sorry. Has u showed up anywhere? No, it hasn't, right? Because we still have, you know, the highest term we get is bm times this, right? Times. Okay. So what happens if I differentiate once more? Sorry. And remember, this was bm xn plus 1, which is b0 x1 plus bm xn. So what happens if I differentiate once more? Okay, this was the last term, bm, is multiplying xn, right? So if I differentiate this term once more, this last term bm is going to be multiplying xn dot, okay? In other words, the last line, right? So in other words, z to the m is equal to u plus a bunch of things, because the last line u appears, right? So by differentiating, I keep pushing this shift register. If I differentiate exactly the number of zeros here, I get bm all the way to the right. So that term is bm xn. If I differentiate this once more, I find the last line of the equation, and therefore I find u. Okay? So what does it say? It says that if I have this system, which was originally in this transfer function form, I take the output of this transfer function, z. If I keep differentiating z, to find u, until I find u, I'll need to differentiate exactly n minus n times, right? So in other words, if you have a transfer function, and you're wondering, I have the output of this transfer function, how many times do I need to differentiate this transfer function for u to appear? It's exactly n minus n times, okay? And you could also think of it dividing polynomials and things like that, but here you can see it immediately if you want. So the number of differentiations of z4 required for u to appear is the relative degree of the transfer function. Okay, which is not a surprising result. Again, you could think of it as dividing polynomials. So what happens now? Suppose we do this, okay? We differentiate until we find the input. And then we design based on this, right? So this we're going to call V. Right? What's going to happen? Well, we're going to create a stable, hopefully, if we design V well, which should be easy, right? We're going to create a stable n minus nth order closed loop dynamics, right? Which will give me Z. And whose input is 0, or if there were disturbances added to U, you would have this input. Okay. So you have a stable nth order closed loop dynamics, which gives me Z. Now, if I want to get the rest of the states, or the rest of the dynamics from this, okay, so an nth order dynamics, to give me x1, okay, the first component of x, right? X is x1, x1 dot, and so on. Or small x if you want. So how do I get, what is this nth order dynamics that gets me x1 given Z? I've already written it. The question is, where is it on this board? Well, it's here, right? This equation can be written b0x1 plus b1x1 dot plus bmx1 to vm equal Z. Right? Remember, when we talked about sliding variables, we said, we have s equal x dot plus x, but you can also write it as x dot plus x equal s, right? Same story here, okay? This equation, which is how you compute x from z, sorry, as you compute z from x, can also be written this way, okay? And therefore, what's the transfer function of this nth order dynamics? What is this nth order dynamics? Well, it's this, right? What happens if we take the transfer function from z to x1? Well, we just get 1 over b0 plus b1s plus bm sm. Right? If you see this differential equation with input z and output x1, right? That's exactly what you get. So now, why is it that in our two very simple toy examples, we had said that if the system is minimum phase, it's okay. If it's not minimum phase, it's not. Well, precisely because that's what the structure we have. This is the leftover dynamics, if you want. This is dynamics once we've done all our little games with z to the m equal v, right? That's the leftover dynamic, z to the n minus m equal v. That's the leftover dynamics. That leftover dynamics is stable if and only if all the zeros of the original system, which are the poles of the leftover dynamics, are in the left half plane. And therefore, this leftover dynamics is stable if and only if the original system had all its zeros in the left half plane, in other words, was minimum phase. Okay? So you see you have this structure. You have z, you differentiate z n minus m times exactly the relative degree to finally find the control u. You design everything based on this. You have a leftover dynamics, which is given precisely by your companion form, right? This leftover dynamics, you see immediately that its poles are exactly the zeros of the original system. And therefore, this leftover dynamics will be stable in this linear case, if and only if the original system has all its zeros in the left half plane. Okay? Now, notice, and I've already kind of briefly alluded to this, this is in the same family of ideas, if you think of it, as these notions of composite variables, sliding variables, and so on, right? Because what do we do when we define a sliding variable? We define a variable s, right, whose relative degree is 1, right? We'd say we need to differentiate once to get u, all right? So the dynamics of s will be here, and it will be a first order dynamics, right? And then the dynamics from s to x is the leftover dynamics. But in the case of the choice of composite variable, we chose it to be the stable dynamic that defines s. Okay? But you see the general structure is very similar, right? Here we have, say we have a system, we find a relative degree n minus m, and then we have this leftover dynamics. When we play with composite variables, sliding variables, we say, let's pick the leftover dynamics to be nice and stable, and such that the relative degree for it is 1. Okay? But it's the same family of ideas. It's not the same idea, but the same family of ideas. Okay? You see, it has close similarities. Okay? Okay, questions about this? All right, everybody understands also the analogy, this analogy with S, right? Yes?
So given a system, we basically choose an output, which is a combination of these states, and then we say that instead of controlling all the states, we control this output?
Yeah.
Is that the
Yes, and then you wonder whether if you do that, the leftover dynamics is stable, okay? And I was saying in the case of that we did when you pick a composite variable to be stable and then you control that, okay? You end up with a very similar structure, okay? But you do it the other way around, okay? You make sure that this works, okay? And then you leave yourself with first order dynamics so that it's easier to do robust things and so on. Okay. So in the case of composite variable, we have first order dynamics here, which gives us s dot contains u, right, as we wanted. And the leftover dynamics is the definition of s. Okay. All right. questions about this? Yes.
So if they have the same structure, why would you not choose to do it in a composite variable form when you're guaranteed that the dynamics could be stable afterwards?
Well, here we're trying to understand more about the structure of systems. Okay, so we're just saying, well, let's pick this variable z arbitrary for some reason. Okay, maybe that's the one you wanted to control originally. Okay, and see what happens if we do that. Okay, but of course, you can of course then next combine both. You know, once you have your system in transform form, you can apply robust techniques to it and so on. But what I'm saying is that when we see something like this, is not a completely unfamiliar idea because we've seen something very similar, but in a different context, you know, in a different design context earlier. Okay. The same way, but later on when we talk about what's called backstepping, we'll see that we've seen a very similar idea before in the context of adaptive control, okay. But it's different story. Questions? Okay, so here, this whole chapter, right, this whole series of lectures, right, is about just understanding the structure of systems, right? Okay. So, now, of course, as I mentioned, one of the reasons for doing this, and again, you know, you have all the historical background explained in the book, but one of the reasons and references, one of the reasons for doing this was that to try to, of course, do this more generally for nonlinear systems. Incidentally, you know, in passing, this says, suppose you have this very big linear system, and you're trying to control x1, and you have x1 dot, and u shows up in the B matrix, right, in the first line. It's actually okay to just control based on the first line, you know, forget about everything else, if the system is minimum phase. Okay, in what sense? It means that the leftover dynamics will have to do with the zeros of the system, which you don't control, right? So it will be more or less fast and so on based on the zeros of the system, at least it won't blow up. Okay? So might even be a useful result, you know, in a very large system, which you know to be minimum phase, right? It's okay to do this, actually. So, now, so how can we extend this to a nonlinear system? So this leftover dynamics, not surprisingly in this case, is called the zero dynamics. Okay, so the zero dynamics, or more precisely here, the zero dynamics is the dynamics not b0 and so on equals z, but b0 x1 plus bm xm equals 0. Okay. So that's the zero dynamics. And that corresponds, of course, to making z equals 0 here. Now, in the linear case, we know that we make z tend to 0, right? So if the zero dynamics is stable, the leftover dynamics will be stable as well, okay? So in the linear case, if you have a stable zero dynamics, then you'll have basically the internal dynamics will be stable or bounded. Nothing wrong will happen, if you want, to the leftover dynamics. As z tends to 0, so will x1. Okay, so if you put a z here, z tends to 0, you have a stable filter, everything tends to 0. Okay. And this internal dynamics, the leftover dynamics, is also called the internal dynamics. Now, in the nonlinear case, you have to be a little careful, first of all, because you don't have a transfer function, okay? But you can still define a zero dynamics, okay? So linear, we've just seen, okay? We've just done that, okay? Nonlinear, you can still define the zero dynamics, which is the leftover dynamics corresponding to the unique u of t that makes z equals 0 all the time. Okay, so in other words, it's very similar to this remark. Because you have z to the n minus m equal v, okay, and you can design the input, there is a unique choice of v and therefore of u that makes you stay at z equals 0 exactly, okay, for the exact same reasoning as here. Right here it was on the entire system. Here is on the first n minus 1 derivatives, okay? But it's exactly the same reasoning. You have z to the n minus 1 equal something, equal v, okay? V is itself, you know, a function of something and u. If you force z and its derivative and all the system to be 0, then it will define uniquely x equals 0. We might as well actually just to be more specific, that makes the state equals 0. So now the problem is, so in other words, this is the zero dynamics, okay? In other words, that's the dynamics which corresponds to being at 0. Now, so it's well defined because it corresponds to unique u of t, all right? But the problem is, in general, and we won't get too much into the detail, but the fact that having a stable zero dynamics does not imply a stable internal dynamics. Why? Because here you had a linear system. If you had z here that tended to 0, you had something that tends to 0 into a stable linear system, so everything tends to 0. Okay? But in a nonlinear systems, more complicated things could happen. Okay? So in a nonlinear system, it's not in general true that if the zero dynamics, which corresponds to very specific value of z, if you want, is stable, then the rest of the system will be stable. Okay? Now, of course, the reverse is obviously true, right? Because the internal dynamics is like the zero dynamic plus something, right? And the zero dynamics is a particular form of the internal dynamics. So it's not easy, therefore, to extend the notion of minimum phase to nonlinear systems because that implication is not true. You can say, I have a nonlinear system, the zero dynamics is uniquely defined. I'm going to say that my system is minimum phase if it's uniquely defined zero dynamics is asymptotically stable. I can do that. It's a definition. Okay? So the definition that many people give, actually, minimum phase nonlinear system is going to be such that the zero dynamics is asymptotically stable. But it doesn't mean that the internal dynamics will always be bounded or working or so on. Okay? So it's just a definition, if you want. But and you can say things more precise, but you know, basically you have this definition. However, it can kind of work the other way around. Okay, so in other words, it's an easy thing to possibly show that things don't work, that the leftover dynamics is unstable. Okay, so if the zero dynamics is unstable, okay, then of course this is not going to work. Now, if you linearize the zero dynamics of the nonlinear system, right, you're going to have a linearized zero dynamics. And of course, the zero dynamics of the linearized zero dynamics is the zero dynamics of the linearized system. Okay, because linearization. Okay. So if the zero dynamics of the linearized system is unstable, then you know it won't work for the nonlinear system. Right? Because if the linearized system, if the linearized the zero dynamics of the linearized system is unstable, then at least locally the nonlinear system will be unstable. Okay. So the brief summary, if you want, is very clear story in the linear case. In the nonlinear case, you can uniquely define something called the zero dynamics. Okay. That dynamics may be, for instance, asymptotically stable or whatever. You may define saying, I'll call my nonlinear system minimum phase if the zero dynamics is asymptotically stable. Okay. But that doesn't really imply general things about the internal dynamics, which is really what you care about. It works to show that things don't work. Okay? In other words, if the zero dynamics of the linearized system is unstable, then, of course, forgetting about the leftover dynamics won't work for the nonlinear system. Okay? So from here on, we're going to go in two directions. Okay? One, we're going to state, and again, zero proofs, okay, just state the general result, saying, take a nonlinear system, and when can you transform it so that basically you can get into this form? Okay. And again, the proofs are in the book, but to really understand the proof, I think you should pick a differential geometry book and start getting really familiar with the concept, and then kind of read this. So that's one direction. The other direction is to say, okay, we've done all this already, we've differentiated, we found the control input, there's a leftover dynamics. Perhaps at least we can say, okay, well, now I have a system which looks a little simpler. I have a system where I've differentiated, I found the input, and I have this smaller order leftover the dynamics. Okay? It's still nonlinear, it's all these things, okay? But the system is simpler. Okay? And so we'll see a technique which is called backstepping, okay, well, although this is not the original name it was given, it's a name that was given to it later, but we'll see a technique called backstepping, which basically tries in some classes of system to do this, okay, to say I have my transform system, it looks like x to v n minus m equal v, and then I have this leftover dynamics, and I'm going to try to design some Lyapunov base kind of controller for this system, but using the fact that it's in a slightly simpler form, it is in a simpler form than the original system. Okay? So these are these two general directions. Okay. So the next hour is going to be the mathematical part of the course. Again, we won't do any proof, but even so, just to define things. But it will give us the central result, if you want, of this whole theory. Okay, so what's the story? What are we trying to understand? We're trying to understand whether or not it is true that if we can start with a system x dot equal f of x plus b of x times u, can we find a smooth invertible state transformation z equal z of x, or to be just a little more formal, we could use a different notation, just let's say z equals z of x, okay? Such that the vector z is of the form of a variable z1 and its derivatives up to order exactly n minus 1, where n, of course, is the order of the system. So can we find a state transformation z equal z of x, where the new state is in this form we like, okay, a scalar and its derivatives, okay, and z to the n, z1 to the n equal v, where u can be computed back from v, assume as u equal alpha of x plus beta of x times v. All right? So can we find a state transformation from this original nonlinear system of dimension n such that the new state is in this form of a scalar and its derivative up to order n minus 1. And the derivative, the nth derivative, the derivative of this last term, is equal to some v, where if we have v, we have u. Okay? So basically the question we've been asking, okay, just stated a little more formally. And by the way, the number of differentiations in a nonlinear system to find u, we can also call it the relative degree of relative order. Okay, that's fine. Okay. So this is saying that the relative degree of the system with respect to z1 is exactly n. Okay. So instead of saying this, right, we could say, can we find a variable z1 such that the relative degree of the system with respect to z1 is exactly n, right? That would be equivalent basically to saying all of this, right? It says we can find a variable such that if we differentiate exactly n times, we find v. Okay. Notice in the so that can be defined in a nonlinear system. In a nonlinear system, you have to be a little more careful, and there's some literature on that, which is also cited in the book. In the fact that, for instance, this relative degree, when you find the control, may actually depend on the state itself, right? Suppose that you differentiate and you find sine x times u, right? Well, you found the control, except when x equals 0 or 2 pi, right? Then it doesn't work. Okay? So you have to be a little careful about that. Okay. But at least you can define, for instance, the relative degree in some region of the state. Okay. And again, there's lots of literature on this particular point. So, for this, we'll need a number of mathematical tools. But you see, we're trying to find the z1 such that its relative degree, or the relative degree of the system with respect to z1, is exactly n. So basically, what we need to do is find a formal way, a symbolic way to do this recursion, right, based on f and g. Right? We're going to say, well, does there exist a z1 equals z1 of x, and we'll define it, we'll differentiate it, and so on, okay? And we need to keep track of notations. We need to keep track of f and g as we keep doing this, okay, if we want to get a general form. All right? Like, you know, computing a Jacobian on a real system, you can just compute it directly, right? But if you want a general form, you say it's df over dx, right? So let's define a few things, okay? So if we have a scalar function of the state x, we'll denote by gradient h, well, it's the gradient, okay, as a row vector. It's a convention you also have in optimal control, okay? So it's dh over dx1, dh over dxn. Right, so it's just a gradient. Now, if we have what's called a vector field, with this very graphic idea of having, you know, at each point in the state space, you put a vector, okay, so vector field. What we'll call this will just be the Jacobian. In other words, it will be the matrix, of course, of components dfi over dxj. Or we can also see it as piling up, as we said before, the gradients of the individual components of the vector field f. Right? Remember, the Jacobian is df1 over dx1, df1 over dx2, and so on, right? So it's basically the gradient of f1 and then the gradient of f2 and so on in lines. Okay, so that's what we have. There's nothing really new here. Just as a term, this notion of smooth, or at least once differentiable and invertible, will be called a diffeomorphism. It's just if you see this term, right? It's smooth in the sense, actually, of a restricted sense of being differentiable once with a continuous derivative, with an inverse, which is also differentiable once with a continuous derivative. Okay, so that's not very new. So what is, though, is what comes next. So, suppose you have a scalar function, okay, h of x, and a vector field, vector which depends on states, the state x. What's called the Lie derivative of h, the scalar function, with respect to f, the vector field, is a scalar function. That scalar function is written as LFH. And it's simply the dot product of the gradient of h times f. Okay. So if you want, maybe in some slightly older vocabulary, it's the directional derivative of h along the direction of f. Okay, so the dot product of the gradient of h times f. All right. Now, why give it a name? Why not give it, just call it gradient of h times f, which is not very complicated? Because we want to be able to define recursive Lie derivatives. Okay? So what we're going to do is we're going to say that LF0 of h is h. LF1 of h is LFH is gradient of h times f. And LF2 of h is going to be simply equal to LF of LFH, right? So let's maybe make it more general, right? So LF n of h will be LF of f LF at minus 1 of h. And therefore will be equal to gradient of LF n minus 1 f, h, sorry, times f. All right? So this allows to define recursive Lie derivatives. Okay, repeated Lie derivatives. Which are basically obtained by taking these, always this dot product of what you have times f. So why could this be useful? Because, for instance, suppose we have x dot equal f of x. And we have y equal h of x. And we're trying to just keep differentiating y. Okay, so here is no control input, just to make things very simple, but let's just keep differentiating y. What do the recursive differentiations of y look like? Well, y dot, right, is dh over dx times x dot. So it's dh over dx times f. In other words, it's precisely LFH. Right? So if you have x dot equal f of x, y equal h of x, scalar, right? If you compute y dot, you get exactly LFH, okay? And not surprisingly, if you get y double dot, you'll get LF2h and so on. Okay? So basically, if you want, this is just a notation to, well, at least here, it's just a notation to keep track of what the derivatives of our scalar look like in terms of f and h. Okay? And similarly, of course, if you had the Lyapunov function for this same system, v of x, right? And you wanted to compute v dot, which we know is v dot of x, right? Because it's autonomous system. This v dot of x will be LFV, of course, for the same reason as this. Okay? Okay. So these are used extensively in the proofs for obvious reasons, because they keep, track of recursive differentiation. So that's the Lie derivative of a scalar function of the state with respect to a vector field. Now, there's another operator which is called the Lie bracket of two vector fields F and G. So the Lie bracket of F and G is another vector field, right? So the Lie derivative of a scalar gives you a scalar. The Lie brackets of two vector fields give you a vector field. And this vector field is simply Jacobian of G times F. Well, simply is not very reasonably simply, Jacobian of G times F. Okay, so you see this is, if you are in coordinates, this is a matrix times a vector minus a matrix times a vector. Okay, so it's a vector. And so Jacobian of G times F minus Jacobian of F times G. All right. Be careful, by the way, if you do get into this field in detail, and therefore, as I suggested, start by opening a good book on differential geometry. Often the definition is the other way around. Okay, but this is the definition which is always used in control theory. Okay, so that's. Okay. So two operators, two new operators, if you want. And then one more definition. Suppose we consider a linearly independent set of vector fields. F1, F2, Fm. Okay, so what does it mean they're independent? It means that there's no linear relation between them. You cannot compute any one of them by taking the others and putting scalar, perhaps state-dependent coefficients. Right? So there's no linear combination between them. Okay, so linearly independent vector fields. The scalars could be state-dependent, right? Okay, so you start with this, okay? This linearly independent set of vector fields, okay, or family of vector fields, is said to be involutive if, and only if, it's a definition, whenever you take the Lie bracket of two elements of this field, you can always write it as a weighted sum, weighted by scalar coefficients, perhaps state-dependent scalar coefficients, of a weighted sum of the vectors fields in the family. Okay, so Fk of x. Right? So think of it, this is related, if you think of it, to controllability, to the reachable space, if you think about it, right? It says you have a family of vector fields. We'll come back to that, right? But you have a family of vector fields, okay? And so it can span a space, okay? It's linearly independent, okay? So it spans some kind of space by taking all the possible linear combinations of these vector fields, all right? So you find some space, okay? Saying that this family is involutive, the family that spans that space, right, is involutive, is saying that if you take the Lie bracket of any two of the components of the family, you're still in the same space. You don't get out of the space, right? You don't explore anything else, right? So it's saying, in a sense, taking the Lie bracket won't take you to new places. Okay? So that's what the definition of involatility is. And as we shall see, without getting into the details, okay, but this is related to something called Frobenius theorem, which shows that this involatility is related to the integrability of certain equations, okay, the fact that they have solutions. So here we are, okay, for the moment we've just defined things, okay, so gradient, Jacobian, that we knew, Lie derivatives, Lie brackets, okay. So now we have all the elements, all the definition, just to be able to state the main theorem, okay, which we'll do next time. We won't prove it, okay, we'll just state it. And we'll interpret it also. We'll see that it comes, with two conditions, and these conditions can be well interpreted. And the main point of this theorem is that it's a necessary and sufficient condition. All right? In other words, it doesn't tell you, well, if you can do this, then you'll be able to. If you cannot, well, maybe there's another way, okay? It tells you this, if I have this question, okay, is it possible to find a new state such that the relative degree of Z1 is exactly n? There's actually a necessary and sufficient condition for that, which comes in the set of two conditions. Right? And that's the central result of this whole field of feedback transformation. Okay? So that's what we'll see, not next time, because next time is the quiz, right? It's the preparation to the quiz, but that's what we'll see afterwards, okay? And then we'll do something which is a little more benign, which is the other direction I was talking about, which is to say, without doing this, just differentiating until we find an input, let's use the simplified system and try to do something the Lyapunov way with it.